Okay, last chapter or last section in this chapter talks about the derivative, which is another concept from calculus that you're going to talk about a lot in calculus. And as I said in the introduction to this chapter, there's a lot of algebra involved in calculating derivatives, and it's oftentimes that algebra that ends up tripping students up, which is why I want to briefly introduce you to the derivative. I'm not going to give you a ton of uh, detailed information about the derivative. I just want to be able to practice the algebra involved with calculating derivatives, and so that's going to be the focus here. But you'll talk about all kinds of applications of the derivative and uh, various ways to define the derivative and things like that in calculus. We're just going to go for a pretty intuitive understanding. So let's get started. Suppose that your salary in 2006 was $25,000 and that your salary in 2011 was $40,000. What is your average increase in salary per year? So we could find this out pretty easily, right? The average increase in our salary per year. Well, how many years passed, right? Between 2006 and 2011, that was 5 years that passed by. And what was the increase in your salary? Well, it looks like your increase was $15,000. So, so your salary increased $15,000 in a 5-year period of time, right? So you had a $15,000 increase in 5 years. So the average increase per year, we would say, would be 15,000 divided by 5 years, which is $3,000, right? So it's $3,000 per year, right? That was the average increase in your salary, $3,000 per year. We can think of the previous scenario in terms of functions as follows, right? So let f describe your salary as a function of the calendar year. Then in that case, f of 2006 is 25,000 and f of 2011 is 40,000. The average increase in salary can then be described as f of 2011 minus f of 2006 divided by 2011 minus 2006, right? Because f of 2011 would be the 40,000 that you ended up with. F of 2006 would be the 25,000 you started with. So it's the change in your salary divided by the change in years, right? You get 3,000, just like we said before. So in general, if f is a function and a and b are in the domain of f, then we say that the average rate of change between the points a, f of a, and b, f of b, is f of b minus f of a over b minus a. That's the average rate of change between these 2 points. Okay? Now, note that we can describe b in terms of a by saying that b equals a plus h for some real number h. Okay? So in other words, right, if a is here and b is there, then you can just say that b equals a plus h for some value h, right? So if we replace b with a plus h and f of b with f of a plus h, then we obtain this, right? We get f of b minus f of a is really going to be f of a plus h minus f of a. And b minus a is going to be a plus h minus a. And we can combine like terms down there in the denominator. We would get f of a plus h minus f of a all over h, right? The a's cancel. This quantity, I guess this expression, is called the difference quotient, right? So the difference quotient is the average rate of change between the points a, f of a, and a plus h, f of a plus h. Okay. it gives us the average rate of change between those 2 points, right? Now in calculus, the whole thing with derivatives in calculus is that we want to know what the instantaneous rate of change is at a particular point. So instead of trying to find the average rate of change between 2 points, we want to know exactly how fast the function is changing at one point, right? At a particular point. In other words, we want to know this limit, right? We want to calculate the average rate of change as h goes to 0, right? As the distance between the 2 points goes to 0, right? As the distance between the points disappears and the points become just a single point, right? So we want to calculate this limit. Okay? If that's confusing to you, don't worry about it too much at this point. You're going to go over this in calculus and get a really good understanding of what the derivative is, okay? But this is the derivative, okay? So I'm just trying to give you some kind of motivation for understanding what the derivative is. It's the instantaneous rate of change at the point, in this case, at the point A, right? So, so that's our definition. That's our working definition of the derivative. We'll say, let f be a function and let a be in the domain of f. Then the derivative of f at x equals a, we'll use this symbol to denote that. We'll call this f prime of a, right? This is the derivative of f at x equals a, right? F prime of a is this limit, right? F prime of a is the limit as h approaches 0 of f of a plus h minus f of a divided by h. Provided that the limit exists, right? The limit may not always exist, in which case the derivative doesn't exist at that point. Let's practice this. So let's say that f of x is 3x. Let's find f prime of 2, and then let's find f prime of x. Okay, so f prime of 2 is a particular case. And then f prime of x, of course, we're not going to get a number. We're going to get a function. Well, actually, in this case, we will get a number, but it'll be sort of a more general thing. So f prime of 2. F prime of 2 is equal to the limit as h approaches 0 of f of, well, it's f of a plus h, but in this case, a is 2, right? So it would be f of 2 plus h minus f of 2 over h. Okay, so that's the limit as h approaches 0. Well, let's think about what f of 2 plus h is. F of 2 plus h, that would be 3 times 2 plus h. Okay. F of 2 would be 3 times 2 all over h, right? So f of 2 plus h, we just look at f of x, and everywhere we see an x, we replace it with 2 plus h. So instead of 3x, we have 3 times 2 plus h. F of 2, right? F of 2, we look at f of x, everywhere we see an x, we replace it with a 2, right? Okay, let's simplify. Limit as h approaches 0 of 6 plus 3h minus 6 over h. So this is limit as h approaches 0. Obviously, if we plug in 0 right now, we're going to get, something over 0. That's going to be undefined. So our goal really is to try to cancel the 0 in the denominator if we can. And in this case, look what happens, right? The 6's cancel. We get 3h over h. And then the h's cancel. We get limit as h approaches 0 of 3. That's kind of strange because we're looking for the limit as h approaches 0, but there's no h left over in the expression. Well, if there's no h left over in the expression, then this should just be 3, right? It doesn't matter what h is. This expression is always going to be 3. So there you go. F prime of 2 is equal to 3. We can use that same idea to find f prime of x in general, right? F prime of x is limit as h approaches 0 of f of Well, if f prime of a is f of a plus h minus f of a, then f prime of x is going to be f of x plus h minus f of x divided by h. Now, if I want to find what f of x plus h is, I would look at f of x and replace the x with an x plus h. So I'm going to get 3 times x plus h. F of x is just 3x. So we get 3x plus 3h minus 3x over h. And look at that. Same thing as before, right? The 3x's cancel. And then the h's cancel. So with no h's left over in the expression, we just say, well, limit as h approaches 0 of 3 is just going to be 3. Okay. So in this particular case, with this particular function, f prime of x is always going to be 3, regardless of the value of x, right? So f prime of 2 is 3, f prime of -1 would be 3, f prime of 0 would be 3, right? Any value you like is going to that you'd like to plug in here, f prime of that value is going to be 3. Okay. That doesn't always happen with derivatives. It just so happens to happen here. Okay. Let's do another example. So let's say that f of x is x squared. And let's do the same thing. Let's find f prime of 2, and then let's find f prime of x. So remember, right? F prime of a is the limit as h approaches 0 of f of a plus h minus f of a over h, right? That's the definition. So let's see, f prime of 2. This should be limit as h approaches 0 of f of 2 plus h minus f of 2 divided by h. Now what's f of 2 plus h? Well, we're going to look at f of x, and everywhere we see an x, we're going to replace it with a 2 plus h. So we're going to get 2 plus h squared. All right, that's f of 2 plus h. What's f of 2? Well, we're going to look at f of x, and everywhere we see an x, we're going to replace it with a 2. So f of 2 should be 2 squared. Let's see what we get. 2 plus h squared. Now, I've mentioned this in this class before, and this is going to be a common theme, but like a plus b squared does not equal a squared plus b squared. It'd be nice if it did, but this is called the freshman dream. Because freshmen in college who are taking like their first calculus class or whatever, they want to believe that this is true, but it's not, right? A plus b squared, well, you have to FOIL that, right? You have to write that out twice and then FOIL it. And if you FOIL it, you discover you get a squared plus 2ab plus b squared. So you're missing this middle term if you just try to distribute the exponent, right? The exponents do not distribute across addition. So same thing's going to happen here, right? If we want to do 2 plus h squared, it's not 4 plus h squared, right? This is going to be 4 plus 4h plus h squared. Okay, and then the 2 squared is 4. Now the 4's cancel. And from the numerator, I can factor out an h. If I factor out an h, I'm left with 4 plus h. And then these h's cancel. Notice that this time, not all of the h's get completely canceled off, but I did manage to cancel off the h in the denominator, which is good. That's what I need to be able to do in order to be able to calculate this limit. Because now I can say, okay, limit as h approaches 0, I can just plug in that 0. And as long as I have something that's defined, that is the limit, right? That's what we discovered in the previous section on the last page. So if I just go ahead and plug in 0, I'm going to get 4 plus 0, which equals 4. Right? So f prime of 2 would be 4 in this case. Let's see if we can employ that same strategy to find f prime of x in general. So f prime of x is going to be limit as h approaches 0 of f of x plus h minus f of x divided by h. That's going to be x plus h squared minus x squared over h. That's going to be x squared plus 2hx plus h squared minus x squared. Right? This stuff comes from that, right? From expanding that. And then divide by h. The x squareds cancel. The x squareds cancel, and I can factor out an h from what's left over. I get h times 2x plus h. Right? That's gone, and then from here I can factor out an h. If I factor out the h, I'm left with 2x plus h, right? And then the h's cancel. And that finally gets rid of that h in the denominator that was messing us up, right? So then we get 2x plus h. Now I can plug in 0. I get 2x plus 0, which of course just equals 2x. All right, so in general, f prime of x is just going to be 2x. So if f of x is x squared, then f prime of x is 2x. Now what's interesting about this is that if we know that f prime of x is 2x, then another way to find f prime of 2, right? We found f prime of 2 before and we saw that it was 4. Well, now that we know that f prime of x in general is 2x, we could find f prime of 2 by just plugging it in to this function, and sure enough we get 4 just like we did earlier. Okay? So this is the idea behind the derivative. This is all I'm going to give you for now, but we're going to practice calculating derivatives as we move through, especially chapters 2 and 3, okay? And really, especially chapter 2 more than anything. So we're going to talk about derivatives of specific kinds of functions as we move through those sections, so that we can practice the algebra involved here, okay? For now, let me just give you one motivation for why we're interested in derivatives. You may have heard that calculus was invented by Newton, and that's Isaac Newton, right? And that's partially true. Newton developed a lot of the things in calculus kind of simultaneously with a couple other people. They were all kind of working on this unbeknownst to each other. But anyway, Newton's perspective, when he was developing calculus, it was because he wanted to understand physics, right? Newton was a great physicist, like probably the greatest physicist of all times, arguably, I guess. You can maybe throw in like a couple other people into that mix, you know, Einstein and whatnot, but Newton was a great genius, right? And he was really the father of modern physics. But he wanted to understand physics better, and calculus turns out to be really, really useful to understand physics, right? So one of the ways that calculus comes in physics, and the derivative in particular, is as follows. So you may remember from previous algebra classes, or if you had physics in high school or something like that, you may remember that the height of a projectile t seconds after it's launched is given by this function, right? So the height, we'll use p for position, I guess, but the height of the function is negative 16t squared. That negative 16 is just the gravitational constant, so it accounts for the gravitational pull. So this is assuming, of course, that you're launching this projectile on Earth. If you were launching the projectile on the moon, then you'd have a different constant here. All right, but it's negative 16t squared plus v naught t. V naught is the initial velocity with which the projectile is launched, and then plus s. S is the initial height from which the projectile is launched. So if you're launching from the ground, s is 0. But if you're launching from like a platform 20 feet above ground or something, then s would be 20, right? So, for example, suppose that a rocket is launched from a platform that is 10 feet off the ground with an initial velocity of 110 feet per second. Part A asks us to write down the function, p of t, that models the height of the rocket after t seconds. So p of t is going to be negative 16t squared plus the initial velocity. The initial velocity we said was 110 feet per second, so 110t. Plus the initial height, which we said it was launched from a platform 10 feet off ground, so the initial height is 10. Okay, so this function tells us how high the projectile is from the ground after t seconds. For example, what's the height of the rocket after 4 seconds? Well, we would just plug in t equals 4. I'm just going to use my calculator. Negative 16 times 16 plus 110 times 4 plus 10 is equal to 194. So 194, right? That's the height of the rocket after 4 seconds. So 4 seconds after it's launched, it's 194 feet from the ground. Okay, so that's how this function works. Now, note that the projectile does not move at a constant velocity. Its velocity is always changing. Okay, when it's initially launched, using the previous example, it was initially launched at 110 feet per second. But as soon as it's launched, gravity starts to pull it back down towards the Earth, right? Gravity starts to work on it. And so its velocity decreases and decreases and decreases until eventually the projectile reaches its maximum height, and then it starts to fall, right? So the projectile does not move at a constant velocity. Its velocity is always changing. So if we wanted to answer a question, so we can use this function, of course, to answer, we can use this function to answer the question, how far is the projectile from the ground at any given moment in time? But if we wanted to figure out how fast is the projectile moving at any given point in time, well, how would we figure that out? Let's think about it. So how would we figure out how fast the projectile is moving at, say, t equals 3 seconds? Well, one thing that we could do is we could compute its average speed over smaller and smaller intervals to see what speed we approach. In other words, we could compute the derivative, right? We could compute the derivative of the position function. And that's exactly what we're going to do, right? The velocity function for a projectile. Okay, so the velocity of a projectile is the derivative of its position function. Okay, so let me give you some examples. This one says, a stone is thrown upward from the edge of a bridge 96 feet high with an initial velocity of 40 feet per second. Write down the function that models the height of the stone after t seconds. So the height, the position, is going to be negative 16t squared plus initial velocity, 96 times t plus, 96 was the initial height, right? It was thrown from the edge of the bridge 96 feet high, but its initial velocity was 40. So my apologies, this number should be 40. The initial velocity is 40, and then the initial height is 96, right? So there's the position function. Now part B says find the velocity function. Okay, so for the velocity is the derivative of the position. The derivative of the position is going to be the limit as t approaches, or sorry, not t, the limit as h approaches 0 of p of t plus h minus p of t divided by h, right? That's just the definition of the derivative, okay? So now let's see. This is going to be limit as h approaches 0, p of t plus h. I'm going to look at p of t, And everywhere I see a t, I'm going to replace it with t plus h. So this is more complicated than the ones we've seen before, but let's do it. We're going to have negative 16 times t squared, but t is going to be replaced with t plus h squared, plus 40t, but t is going to be replaced with t plus h, plus 96. Okay, so that's p of t plus h. That's just p of t plus h. Now I need to subtract off p of t. So I need to subtract off the original function, negative 16t squared plus 40t plus 96. And then I need to divide all of that by h. Okay, a lot of simplifying to do here. Obviously, I can't just plug in 0 now because I'm going to get 0 in this denominator, and that's going to be undefined. So I need to do some simplifying to see if I can cancel this h down here in the denominator. Let's see. I'm going to have negative 16 times t squared plus 2ht plus h squared plus 40t plus 40h plus 96. Okay, you with me so far? So I've gotten to the end of this thing. Now I'm going to distribute this negative sign. So if I distribute the negative sign, I'm going to get a plus 16t squared minus 40t minus 96. Okay, let me go ahead and distribute the negative 16t, or negative 16 now. We have negative 16t squared minus 32ht minus 16h squared. And then everything else I think stays the same, but fortunately there's going to be a bunch of cancellations here, I think. One thing that you'll discover is that you cannot be lazy. You really need to write the stuff out or else you're going to get lost, but the negative 16t squared and the positive 16t squared cancel. This 96 and this negative 96 cancel. This 40t and this negative 40t cancel. So all that stuff cancels. Now notice that what you have left are these three terms here. And all three of them have an h in them. So on the next step, I'm going to go ahead and factor out that h so that I can cancel it with the h in the denominator. Okay? So I've got h times negative 32t minus 16h plus 40 divided by h. Now those h's cancel. I get limit as h approaches 0 of negative 32t minus 16h plus 40. Well, as h goes to 0, this term is going to disappear, right? Right? This is just going to, right? I've eliminated the h in the denominator, so I can go ahead and just plug in h now, right? So I'm going to have negative 32t minus 16 times 0 plus 40. Well, that just equals negative 32t plus 40. Okay, so there's my velocity function. There's a train coming. So there's a train track that runs right behind my house, and so the train comes like once a day. Anyway, I'm going to put myself on pause for a second and then move on to the next page. Okay, so this is the velocity function that we just computed based on the position function. So now we can answer a bunch of questions, right? Like part C, how far is the ground from, or sorry, how far from the ground is the stone at t equals 1 second? And how fast is it moving at that moment? Well, I guess I should have written down the position function as well, right? The position function was negative 16t squared plus 40t plus 96, I believe, right? Yep. Okay. So how far from the ground? Well, if you want to answer how far from the ground, then you should use the position function. And if you want to figure out how fast it is, then you should use the velocity function, right? So at 1 second, So let's see. So that would be negative 16 plus 40 plus 96 is 120. So it's 120 feet from the ground after 1 second. How fast is it moving? Well, that would be negative 32 times 1 plus 40. That would be 8 feet per second, which is actually not very fast, right? It's like you see, so you can tell that it's slowed down quite a bit after just 1 second, right? Because remember, its initial velocity was 40 feet per second. So it was initially launched at 40 feet per second, but after 1 second, it's already slowed down to 8 feet per second, right? So there you go, an application of the derivative, right? You can figure out exactly how fast the thing is moving at any particular point in time. Part B, how far from the ground is the stone at 3 seconds, and how fast is it moving at that moment? So same thing, after 3 seconds, negative 16 times 3 squared plus 40 times 3 plus 96. 72 feet from the ground. You may wonder, well, how is that possible? Right? It was 120 feet, but it's because it started to come back down, right? So the stone was thrown, and now it's starting to travel back downwards, right? So 72 feet, which means I suspect the velocity is going to be negative, because if it's moving downward, right, velocity is directional. So if it's moving downward, the velocity is going to be negative, right? So this would be negative 32 times 3 plus 40. Yeah, we're definitely going to get a negative number. Negative 32 times 3 plus 40 is negative 56 feet per second. Okay. So it's moving much faster after 3 seconds than it was after 1 second, but it's moving in the negative direction. In other words, it's moving back towards the Earth. Okay. It's not going to take it very much longer to get to the Earth, right? It only has 72 feet to go before it hits the ground, and it's moving at negative 56 feet per second. So it'll take less than a second, or actually, I guess I'm not sure how long it'll take, but not very long. So that's that. That's all I'll say about derivatives for now, but they're going to come up again throughout the course.